So good afternoon to all of you. In today's lecture, we are going to continue our optical fiber communication modules, and in this we are going to discuss about basic classification of optical fiber. So in this we are going to deal about what are the different categories in which we are going to classify the optical fibers based upon the refractive index, based upon the mode, based upon the polarizations. There are various kind of optical fibers. So we will discuss in detail about these three different categories one by one. So these are the different classification of optical fibers. So based on a refractive index, based upon the variation of a refractive index, especially in the core sections, we have two types of optical fiber, that is a step index optical fiber as well as a graded index optical fiber. Now the second category is as it is a step index optical fiber. The first category as it is a step index optical fiber. So index is basically signifying the refractive index. So variation in the refractive index will follow some kind of variation like a step. That means there will be a sudden change in the variation of a refractive index. Similarly, graded index as we have seen that it is a refractive index. So the variation in a refractive index not going to be a sudden. There will be a gradual decrease in the refractive index as one move from the center axis of the optical fiber. So that's why it is a graded index optical fiber. Now the second category is based upon the modes, that means number of rays that or waves that can be traveled through the optical fiber, and based upon that we are classifying the optical fiber, and it is of two types. First is a single mode and the second one is the multi-mode optical fiber. So if it is a single mode optical fiber, means that there will be a single ray that will be propagating through optical fiber. If it is a multi-mode optical fiber, means that there will be multiple rays that will propagate through optical fiber based upon the phenomena which we have already discussed, that is the total internal reflections. So this is a second category based upon which we can divide the optical fiber. Now the third one is based on improvement in the propagation properties. Based upon the improvement in the propagation properties, there are three types of optical fiber, and first one is a polarization maintaining optical fiber, second one is a dispersion shifted optical fiber, and the last one is a dispersion flattened optical fiber. Basically in this module we will concentrate on the first two categories rather than moving into deeper concept of the third one, although we are going to discuss the overview about what is called as a polarization maintaining fiber, then dispersion shifted fiber, and finally dispersion flattened optical fibers. So our aim is to just concentrate on these two categories, right? So let us try to move into details about these two categories, what is step index and what is graded index. With the help of pictorial diagram, we will going to discuss the concept of the first category. Now this is basically the refractive index profile, I mean the first category, that is a step index fiber. So in this what is happening, as I have already told you that the variation in refractive index not going to gradual. There will be a sudden change in the refractive index, means at some point of a distance it will be constant, and after that there will be a sudden decrease in the variations. So this is what this figure is telling us based upon the refractive index profile. So as we have already discussed, there will be a sudden change in the refractive index. This is the fiber and this is the center axis of the fiber. We already know that this is a cladding and this one is a core. So the central axis of a core, and from there we can see that the refractive index of a core, we all know that refractive index of a core is greater than refractive index of the clad. So the thing is that the central axis of the optical fiber, the refractive index variation at some distance will be constant, and after that there will be a sudden decrease in the refractive index. There will be sudden decrease in the refractive index, and that decrease in the refractive index is occurring at the core and clad interface. So at this point there will be a sudden decrease in the refractive index, and after that till the portion of the clad it will going to continue. So that is called as a refractive index, I mean step index optical fibers. as it is following something criteria of variation in the step. We already know that what is the step, this one is the step, right. So this is your step function. So that means there will be a sudden change in the magnitude, or this is in terms of a signal, there will be sudden change in the magnitude at some point of a instant, and after that it will remain constant and another time of an instant it will decrease. So that means there will be sudden change in the value of the signal. So that is what simply this diagram is also indicating. As we are talking about in terms of refractive index, so we have to discuss the variation of a refractive index following the profile of a step function. So this is the core, we already know that this is core, and we have considered that A as the radius of this core. So the formula is saying that NR, what is NR? NR is the refractive index variation as a function of a radial distance. So that means there will be a change in the refractive index as one move from the, this is your point 0, as one move from the central axis towards the core and clad interface, right. So this is what this one is indicating. It is a function of the radial distance from the center of the axis. So whatever the refractive index variation going to occur as a function, as one move from the central axis towards the clad. So that is what this NR is indicating. Refractive index variation as a function of a radial distance. So this NR is equals to N1 when your R is less than the A. R is the radial distance. When it is less than the radius of the core, then it is your N1, and when your R, that is radial distance, is greater than or equals to the A, then in that case we say that it is a NR is equal to the N2, that is the refractive index of the clad. So this is what this refractive index profile variation, based upon the refractive index profile variation, we saw one type, that is your step index optical fiber. Step index means refractive index, variation in the refractive index as a function of radial distance will be your step function. So that's why the name is step index fiber. Similarly, there is another part of this, there is another category of optical fiber based upon the refractive index variation, and that is your graded index optical fiber. So this is a graded, the word is your graded index, and as we have already discussed, index means that it is a refractive index, right. So means that refractive index variation not going to follow the profile of a step. That means there will be no sudden change in the variation of refractive index. There will be a gradual decrease in the value of the refractive index as one move from the central axis of the optical fiber towards the clad. So this is what this diagram is indicating. In the earlier case, we saw that there is a step change, and then at the core clad interface it decreases to this point and then it remain constant, similarly like this one. So this is your step index optical fiber, but we are discussing about the graded index optical fiber. So in this, what we are seeing that the maximum value of a refractive index will be at the core, right, at the central axis of the core, and as one move from 0 at the central axis of the core towards the clad region, we see that there is a gradual decrease in the value of a refractive index. So that is what this graded index optical fiber meaning is. So that means instead of a constant refractive index throughout the core region, there will be a different refractive index region inside the core axis. As we have discussed in the step index fiber, we saw that there will be a sudden decrease in the refractive index variations. So means that in a step index optical fiber, the refractive index of the entire core region will be a homogeneous. That means it will be a single value. Whereas in the case of your graded index optical fiber, the refractive index variation, that means the material through which this core region is met is in such a way that the different region, or that means as one move from the central axis toward the core and clad interface, there will be a region of different refractive index. That's why there is a gradual decrease in the refractive index profile of the optical fiber. Now, as we have discussed in the case of a step index fiber, the NR, that means refractive index variation as a function of the radial distance, was NR equals to N1 for R less than A. Similarly, NR equals to N2 for R greater than or equals to A in the case of step index profile. Similarly, in the case of a graded index profile, the refractive index variation as a function of a radial distance is given as NR equals to N1, 1 minus NR equals to N1, 1 minus twice of del R upon A alpha to the whole 1 by 2, where this alpha is called as profile parameter. This alpha is a profile parameter, and this delta is relative refractive index variation. What is this delta? Delta, we have already discussed in our previous module. What is delta? Relative refractive index difference. So this is what delta is, and alpha is your profile parameter. So based upon the value of refractive index variation, that means a step, triangular and something like that, the alpha value will be depending upon that one. Now apart from this, we have the next category, that is based upon the modes that is propagating through the optical fiber. The first category is over, that means based upon the variation in refractive index, there was two category, that means a step index optical fiber, there will be a gradual change or there will be a sudden change in the refractive index variation profile as one move from the center axis of the optical fiber towards the clad. Similarly, graded index optical fiber means that there will be gradual change in the value of a refractive index as one move from the central axis of the optical fiber, that means a core, towards the clad region. So these are the two categories of variation in refractive index profile, and the next category is based upon the modes of the optical fiber. What are the different types of optical fiber based upon the modes? So the first one is called as a single mode optical fiber, and the next one is your multi-mode optical fiber. So as this is saying single mode, so that means there will be only one mode that will be, or one ray that will be propagating through the central axis of the optical fiber. That's why it is called as a single mode optical fiber. So this is a single mode optical fiber, and that is basically used for long distance communication, right? As there is only one way, that is ray that is going to propagate through this optical fiber, and based upon the dispersion phenomena, and we are not going into detail about the dispersion phenomena right now because this is not actual time to discuss about the dispersion. We will discuss which kind of a dispersion is going to affect the propagation of a light through the optical fiber, and which kind of a dispersion going to be encountered while through the ray when it propagates through the multimode optical fiber. So this is a single mode optical fiber. Only one mode or only one ray will be propagating through the optical fiber means through the axis of the core. Next category is called as a multimode propagation. So multimode propagation means that there will be a multiple ray that will be propagating through the optical fiber. So instead of only one ray, that is a direct ray that is propagating through the central axis of the optical fiber, there will be many more rays that will propagate through the optical fiber based upon following the phenomena of total internal reflections. So in the earlier case, single mode, there was only one mode or only one ray that is propagating through the optical fiber, whereas in this case there is multiple modes that will be propagating through the optical fiber. Next point is your V parameters. This is the important term that most of the numericals of unit 1 is asked based upon this topic. That means a V number, also called by a name normalized frequency and or a V parameters. So it basically determines, this one is determining how many modes a fiber can support, right? We have discussed the category of optical fiber based upon the number of modes that it can accommodate. The first one is a single mode, as it is accommodating only one mode through the optical fiber, and the another one is called as a multimode. It is propagating or it is supporting multiple modes through its core. So this normalized frequency is telling us, giving us information about a particular optical fiber as how many modes that particular optical fiber going to support, or that particular how many modes that going to propagate through that particular optical fiber. So now what is the formula? The thing is that what is the expression for the V number? So that is your 2 pi a upon lambda under root of n1 square minus n2 square. So this 2 pi a can also be rewritten as 2 pi a upon lambda into numerical aperture, because we know that under root of n1 square minus n2 square is your numerical aperture of the optical fiber. So this is the first expression in which a numerical can be asked. Similarly, this can be the next expression derived from this one, and this can be the next expression, because here a is the radius of the core. So this 2 pi a is there, so 2a is there, that we call as a diameter of the core. So this is written as pi d upon lambda under root of n1 square minus of n2 square. So if it is a numerical aperture, so similarly this formula can be rewritten in terms of the relative refractive index variation difference. So we know that n1 is the refractive index of the core and n2 is the refractive index of the clad. Now, as I have already told in our previous previous slide, that if it is a numerical aperture, so numerical can be based upon that means they are going to give the value of the relative refractive index difference and some numerical aperture of the core and the core radius, as well as they are going to give some kind of a frequency. So based upon the frequency, one can easily calculate the wavelength. So all the parameter going to be given to you, and if you know the formula, then you can easily find V number, that means a normalized frequency, and make a conclusion that how many mode that particular fiber can support, right? So the next thing is that how we can say that based upon the normalized frequency, how we can say that this particular fiber going to accommodate only one mode, or this particular fiber going to accommodate multiple modes. So based upon the V number, so based upon the graph of a B and V profile, we can say that if a value of a V is less than 2.405, then that category of a fiber is called as a single mode fiber. On the other case, if the value of a V number is greater than 2.405, now this value of a V number is something based upon the graph, right? B and V graph. So we can see that we in that graph that we could observe that if value of a V, if we are going moving from the value of a V above 2.405, so that particular fiber going to work as a multi-mode fiber, it's going to accommodate multiple modes through it. I mean multiple modes going to propagate through the core and reach at the destination, that means output of the optical fiber. Similarly, if value of a V is less than 2.405, then we observe that that particular optical fiber is working as a single mode because it is accommodating only one mode through the core axis. So this is value based upon the V parameters. Now the next thing is we are going to analyze the cylindrical waveguide, that means optical fiber as a cylindrical waveguide. So in this is the figure, and in this we are going to discuss the various equations based upon the Maxwell conditions, and we are going to write some expressions, and after that we are going to write the solution of that particular expressions, and based upon that particular solutions we can find how many modes that particular fiber can accommodate. So the thing is that this is the appropriate coordinate system to analyze this problem is the cylindrical coordinate system, and the wave propagates in the direction and the fields have definite distribution in the cross sectional plane defined by r and phi. So we all are familiar with this equations, Maxwell equations, that means del cross B equals to, that means curl of E equals to minus del B by del T. Similarly, del cross H is equal to del D by del T, and if there is no free charge or if there is no free poles, then del dot D equals to 0 and del dot B equals to 0, because we know that del dot D is equal to volumetric charge density and del dot B is equals to 0, right? So the next thing is that this D and E can be written in terms of electric permittivity and the magnetic permeability as D is equal to epsilon E and B equals to mu H. So with the help of first equation and the second equations, if we are taking the curl of those equations, then it can be rewritten as del cross H equals to mu E minus of mu E del 2 E upon del T square. Similarly, the next equation can also be rewritten. Now, then by using the divergence condition for equation 3, this is the equation 3, we can get this expression, and for a non-dispersive media, that means a wave equation can be written as del square E equals to mu epsilon del 2 E upon del T square. Similarly, for the in terms of magnetic field, a wave equation can be rewritten. So this del square term, this del square parameter, this del square expression is also called by a name Laplacian operator for rectangular Cartesian and cylindrical polar coordinates. This above equations hold. So similarly, we know that phase velocity equals to, or phase velocity is inversely proportional to under root of mu epsilon, and mu can be written as mu 0 and absolute permeability and relative permeability. Similarly, permittivity can be expressed as absolute permittivity and relative permittivity. So if we are talking only about the free space, then definitely the velocity of light in free space is written as C equals to 1 upon under root mu 0 epsilon. That means mu 0 epsilon 0 is the absolute permeability and absolute permittivity. So this is the last wave equation that we will get. After that, the solution for this is, the basic solution of a wave equation is a sinusoidal wave, which can be expressed at psi equals to psi 0 exponential of a j omega t minus k r. So another thing is that propagation constant, which is written as beta or k, can be expressed in terms of 2 pi upon lambda, right? So this k is also referred to as a free space wave number. So in our next module, that means in our lecture 5, we will discuss about what is mode, what is the basic definition of a mode, how particular modes can be formed, because we have categorized the optical fiber based upon the number of modes that it can accommodate. So first of all, we should know what is mode. So in our next module, we will discuss about what is the meaning of a mode. So thank you all for attending this session.